All right. Hey guys, how are you? So I'm going to talk about pathophysiology of type 1 diabetes mellitus. Okay, so let me start by saying in general what diabetes mellitus means. Okay, it's obviously a condition that we characterize by essentially absent control of blood glucose by insulin. Okay, and what happens after that? So there is no insulin-mediated blood glucose control. And so what happens after that is that the blood glucose skyrockets. We call it hyperglycemia, okay? And we have definitions how to diagnose it. And all those things are not a part of the pathophysiology, so I'll not tell you, okay? But is studying diabetes mellitus important? Okay, is studying this insulin-mediated blood glucose control problems important? It's very important because nearly 10% of the US population, that's 1 in 10, has one or another form of diabetes, right? Because diabetes is not just one particular disease. It's a problem with insulin production. Okay, that leads to hyperglycemia, too much blood glucose, because insulin is not working very well, or it's not there for some other issues. Okay, so the most common type is type 2. I'll talk about it in another video. But whether it's type 2 or type 1 or gestational diabetes or any other form, right, which are obviously less common, what is definitely true is that anyone who is in the healthcare, anyone who is alive pretty much, will face, patients, friends, family with this diagnosis, right? It's a given. I mean, it's one of the most prevalent problems out there, okay? So, and that's why you get so many questions on NCLEX about diabetes, because all of us face it in our day-to-day lives. Okay, so pathophysiology, as I mentioned, for each one of them is unique, different, but what they do share are the complications. And these complications that they share actually take place over a period of 5 to 10 years. Okay, so over a period of 5 to 10 years, what do you see? You see damage to the heart, damage to the brain, damage to the peripheral vasculature, heart, myocardial infarction, brain, stroke, peripheral vasculature, peripheral arterial disease, right? Patients walk for a few feet, they need a break. Not very good. What else happens? Well, damage to the kidney, very dangerous, very dangerous. Patients lose their eyesight, very dangerous. Why? Damage to the retina, damage to the lens, and there is a damage to the nervous system. So pretty much anywhere you look, right? And don't forget, these damages are due to long-standing and poorly controlled hyperglycemia, right? We're not talking about a very well, a patient who is doing everything that he or she is supposed to do. Now, obviously, it's, treatment's never as perfect as we wish it were, but treating diabetes mellitus will alleviate most of these problems, okay? In type 1 diabetes mellitus, there is an acute, a rather feared complication that's called diabetic ketoacidosis, and I'll probably talk about it in class because it's not a part of the pathophysiology, it's part of what happens after a patient develops type 1 diabetes mellitus. All right, so it's a very feared complication because it leads to death. Okay, so let's briefly talk about pathophysiology of type 1 diabetes mellitus only. And let me start off by saying that it's an autoimmune disorder. So you will also review your immunology to some extent, okay? And let me start by saying that something that, is at a very basic level. All cells use glucose to generate energy. You all know it, right? It's a common sense. It's a It's a fact that everybody knows. All right, so obviously you can derive from there that glucose is an important fuel for our bodily functions because we make money with it. We make the cellular money, that's the ATP. Okay. So how does glucose get from blood to the cells? Well, glucose is provided to cells from the capillaries, right, that surround those cells or are very close to them, kind of bathe them. Okay, so it's cool. So what happens if the glucose level drops and in the blood and it's way too low? Then unfortunately we'll see the patient fall into a coma. That's very dangerous. Now, what happens if glucose level is too high? It can be I've already mentioned it to you right earlier that it can have problems that are acute, like diabetic ketoacidosis. We're talking about type 1 diabetes here, right? Or it can have chronic effects. And I told you that, heart, brain, kidney, or eyes, nervous system in general, right, can be affected. Right? So those are the chronic damages. Well, so it's obviously very, very important for the body to keep glucose levels in blood very tightly regulated within a very narrow boundary, relatively constant levels. It shouldn't go too high, it shouldn't go too low, because too low you have a problem and too high you have other problems, okay? So that was glucose. Now let me talk about something that you've also studied already. Insulin, heard the word, drives glucose into the cell. Insulin drives glucose into the cells. Just a fact that you need to remember because it'll help you to remember what insulin does. So what does it really do? Insulin is the main regulator of glucose in the body, okay? Main regulator. There is another hormone, glucagon, never mind. Is it important? Technically for diabetes, it is very important, but this is supposed to be a very short video. I'll try to keep it within the boundaries, so I'll avoid that. I'm talking about glucagon, okay? So the main regulator of glucose in the body is actually insulin, and insulin is an endocrine hormone. By the way, the name insulin was derived from the Latin word insula. Insula means an island, okay? Insula is an island in Latin. And why is it called an island? Well, because beta cells, and you know what they do. Beta cells are found in the islets of Langerhans, okay? Islets of Langerhans within the pancreas, little islets of Langerhans. You can see them with a microscope. They look like little islets of Langerhans. And islets of Langerhans are part of the endocrine portion of the pancreas. Okay, you know that insulin is released from the beta cells of the pancreas, right? Because beta cells are found in the pancreas. Beta cells release insulin. You've really got to know beta cells. Okay, beta cells of the pancreas. Those are the cells that make insulin. Okay? Now, okay, so if you think about it, so beta cells make insulin, right? And glucose needs to be really, really well regulated. So obviously you would be like in blood, right? So obviously it makes next level sense that, hey, perfusion of those little islets of Langerhans with blood should be very, very good, because how else would you know if there is enough glucose in blood or not, right? And it is true. You would be right, because even though those islets are literally 1 to 2% of the whole pancreas, they get a whopping 20%, 1/5 of all the blood going to the pancreas goes to those islets. Why? Because you got to keep our blood glucose levels within a very narrow boundary, within a very narrow limit. Okay. And why don't I just tell it to you? It's less than 100. Okay, that's what matters. Obviously, above 70, above 80, we usually say above 80. Okay, So, but remember that 100 milligram per deciliter mark. Okay, that's what matters. Don't forget, endocrine hormone means that insulin is released directly from those beta cells of the islets of Langerhans of the so beta cells of the islets of Langerhans in pancreas directly into blood. Okay, and what stimulates it is the glucose level elevation. So as soon as the glucose level rises, like literally within 2 to 4 minutes, you can observe an initial peak in the arterial level of insulin. Okay, insulin to glucose connection is so closely connected. Glucose up, insulin follows with a peak already like a high level at 2 to 4 minutes. Okay, doesn't stay there long. You want to go down because remember, all things that are good within certain limits, right? Glucose is very good. You don't want too much of that. You don't want too little of that. Insulin is very good. You don't want too much of that either. Why? You're going to have hypoglycemia. All that glucose is going to shoot into the cells, okay? Because that's the job of insulin. Right? So what does insulin do? I told you, insulin drives glucose into the cells, okay? How it drives is not so important for pathophysiology of disease directly. Okay? So what's the problem in patients with type 1 diabetes mellitus? The problem is that these patients don't make any insulin, can't make any insulin at all. Obviously, next step, you think, well, without insulin, cells can't really internalize all that glucose. How am I supposed to take all that glucose from blood that is offered to me, right? And I can't take it into the cell. Well, what happens obviously is that cells starve even though they're supplied with all that glucose. So blood glucose level is very high, keeps on rising, for example, after food, right? And the problem is that cells actually starve. So starvation while you're seeing all that food. Why? No insulin. Okay. And as I mentioned, without treatment, diabetes mellitus type 1 is lethal. In fact, just 100 years or just over 100 years ago, insulin was actually identified. And literally within a year, it was recognized to be such an important discovery that those scientists actually got the Nobel Prize. That was the level of recognition. Now, precise pathophysiology of type 1 diabetes mellitus hasn't been really cleared up. But we do know quite a few things already, okay? And newer technology is helping us a lot. But think about it, it's 100 years and we're still trying to find it. So what do we do? What do we know now? We know that pancreatic beta cells in individuals are not the same throughout the population. Okay, so what do I mean by that? Actually, let me walk it back. So we do know that not all individuals have the same predisposition to get type 1 diabetes mellitus, okay? So what do I mean? So if someone is really, really, really tall, right? And they walk through a door, they might actually hit their head, okay? Even like, except if you have like very high ceilings, right? So they're going to hit their head. Why? They're predisposed. Their height, kind of predisposes them. It's a risk factor, okay? Now, type 1 diabetes mellitus patients, we looked at them, we found out, you know what? Their genetic profile actually predisposes them to type 1 diabetes mellitus. They have multiple genetic factors that promote this thing called defects in immune tolerance. And what does that mean? Immune tolerance means what? you see, maybe I should talk about it a little bit later. Okay, so so they have a defect in immune tolerance. They can't tolerate their own self, but I'll go into that a little bit later. Okay? But so they have this genetic problem. They have these genetic factors that predispose them. They're more likely. They're very tall, walking through a short, low ceiling environment. Okay, they are. That was an example. Okay, nothing to do with tall and short for diabetes mellitus. But what do they have? Their problem is that they have multiple genetic factors where they inherit problems, defects in immune tolerance. Okay. Now, what really matters is that when these individuals, not patients yet, individuals are then exposed to an environment that that kind of seals it for them. Okay, for example, a very tall person, would be fine in an environment where ceilings are very high, right? But what if that person goes to some kind of a place where maybe ceilings were intentionally built to be very low? That person is at risk. So these patients with a genetic factor predisposition, genetic profile predisposition, when exposed to, for example, certain viruses, just in June 2022, it was shown that Coxsackie virus B, for example, just one virus, okay? But there are many other enteroviruses, right? Those viruses that live in the gut, enteroviruses that have been associated with a risk to type 1 diabetes mellitus, okay? So environmental factors such as virus, exposure to virus, you carry that virus in you, or you've been exposed to it. So food association to decrease vitamin D, chemicals, medications. What happens to these patients who have a genetic profile that predisposes them to type 1 diabetes mellitus after they're exposed to these environmental factors? And I said that viruses and food and chemicals. Okay, once again, let me say it again. After patients with a genetic profile that predisposes them to type 1 diabetes mellitus have been exposed to environmental factors that are known to cause diabetes mellitus type 1, beta cells of the pancreas in these patients, in these individuals, are destroyed. Okay, so they face basically those beta cells face destruction after exposure to that environment, and this happens because those individuals' immune system turns against them. It turns against them, and it is thought that this autoimmunity may be due to a thing called molecular mimicry. What does mimicry mean? Molecular is obviously at a very small molecular level, right? But what is a mimicry? I mimic what you do means what? You raise your arm, I raise my arm, right? You raise your leg, I raise my leg. Okay, you raise your arm, I raise my arm, and so on. Whatever you do, you blink, I blink. I mimic you, right? So molecular mimicry is a term that says that antibody generator, antigen, any kind of a three-dimensional structure that is capable at a molecular level, that is capable of forming antibodies against it, right? So a small three-dimensional structure, usually containing protein, that enables antibody formation against it, because the body thinks, I don't know you, you're a stranger. I recognize you as a three-dimensional structure that may harm you. So an antigen, this antigenic similarity between microorganisms, so viruses, in this case, maybe medications, that can cause disease, and the beta cells is very similar. Okay, so when a virus has the look of the beta cell, of a part of the beta cell, right? Maybe similar nose, maybe similar lips, maybe similar ears, right? Molecular three-dimensional structure, antigens that are similar. So similar antigens, we call it molecular mimicry. Okay, now this molecular mimicry, presence of this molecular mimicry results in development of so-called cross-reactivity. And you can kind of deduce what it means. It means that the antibody going to kill that virus now sees beta cells and thinks, oh, you got a nose, but that nose looks the same, molecular level, right? Three-dimensional structure. The way you look, three-dimensional, and I'm supposed to kill everything that looks like that, is very similar to the look that I see on the beta cell molecules. And so what does it do? This cross-reactivity leads to an autoreactive immune response. Means what? Autoreactive, you go and destroy yourself, you go and destroy the beta cells. And that's what, and I told you earlier, I'm going to go back to this genetic profile. What did it mean? What did I mean? It's a genetic profile that includes inherited defects in immune tolerance. They don't tolerate, their immune system did not go to school very well. Okay? It did not get taught very well in the thymus, in the bone marrow. And so it kind of, it thinks many things that are actually different look similar. Okay, well-taught immune system would be able to recognize it. You would have good immune tolerance. Patients with diabetes mellitus type 1 have inherited defects in immune tolerance. Okay, they don't tolerate things they should. What things? Their own body. This is a problem with many autoimmune diseases. You all know what strep throat is, right? What is the problem with strep throat that is not treated? Well, antibodies are formed against bacteria, streptococci, but those antibodies go and harm heart and kidneys, even after bacteria are no longer there. So treat strep throat with penicillin ASAP. Why? You don't want to give the body of the patient time to actually make those antibodies. Okay. All right. Now, you've already studied immunology, so let me remind you that there is innate immune system and adaptive immune system. Antibodies, T cells are part of the adaptive immune system, right? So we know that the adaptive immune system has two branches. One is cell-mediated, the other is humoral, right? Well, both of these are actually involved in pathogenesis of type 1 diabetes mellitus. Both of these. So adaptive immune system, type 1 diabetes mellitus. Cell-mediated, yes. Humoral, also yes. Okay, now let's review the hardest type of the hypersensitivity reaction, namely the type 4 hypersensitivity reaction. Okay, it's the delayed type hypersensitivity reaction. Why delayed? It takes about 1 to 3 days to actually see it, right? What happens in type 1 diabetes mellitus, it's also so it's got both cell-mediated and humoral, right? I'll first talk about the cell-mediated component. Cell-mediated is seen as the type 4 hypersensitivity reaction, the so-called delayed, because it appears 1 to 3 days after exposure. So you have this predisposed patient, individual, who has the wrong genes for a healthy, but the right genes for the virus, for example, that sits around and virus says, no, I like that person, patient can get type 1 diabetes. Okay, so this patient will have diabetes mellitus. Now, what happens after exposure to the virus is that there is a direct cellular cytotoxicity. Okay, what does that mean? Cytotoxic T cells, and with the name cytotoxic, obviously they do nothing but kill other cells, cytotoxic, toxic to other cells. Also know them as CD8 positive cytotoxic cells. They go and kill none other than beta cells of the pancreas, beta cells of the islets of Langerhans, the same beta cells that make insulin, the same insulin that drives glucose into your blood is not going to happen anymore, right? So direct cellular cytotoxicity or beta cells die. That's the one way to do it. Another way is the helper T cells. You also know them as CD4 positive helper T cells, the same that are low in HIV, for example, are involved in an inflammatory reaction. It's also a type of type 4 hypersensitivity, okay? Usually study direct cell cytotoxicity. This is the second one, okay? Under the same rubric, technical, inflammatory reaction, okay? So what happens is that CD4 positive T helper cells recognize that antigen, right? That three-dimensional molecular structure. And then it says, I see something's wrong, okay? And you know that that antigen is actually just something that looks like the real deal. Is not. It's a molecular mimicry. So the CD4 positive helper T cell recognizes a self-antigen as a foreign and starts releasing inflammation-mediating cytokines, right? That's not good. So basically it says, I need inflammation. You've already studied inflammation, the 5 signs of inflammation, right? You need to know them. You need to know them cold. Okay, that way you think inflammation, I know what it means. 5 signs, okay? So inflammation-inducing cytokines, what do? They activate macrophages, the big eaters. They also recruit B lymphocytes. So activate macrophages. Macrophages go and eat up whatever is considered worth eating. And among those things are the beta cells of the pancreas. So B cells, B lymphocytes also go there because of plenty of cytokines, right? And B lymphocytes, what they do is they become plasma cells, because for a living, what they do is they make antibodies. Okay. Now, B lymphocytes are in an environment where there is this antigen, right, that looks like the virus or anything that is actually a problem, right, for the body. But now the body was fooled. There is a molecular mimicry going on. So the B lymphocytes make antibodies that are not very highly effective. They go and damage parts of the beta cells. Okay, for example, they damage insulin, for example, within the beta cells, right? Or they make antibodies called anti-glutamic acid decarboxylase antibodies, which you're going to see as anti-GAD, GAD, anti-GAD. And that is important for actually releasing insulin from the beta cells. Okay, so not going to happen. Anti-glutamic acid decarboxylase antibodies. Same problem with anti-islet cell cytoplasmic antibodies. Okay, so basically anti-islet cells, anti-beta cells. And there are many other antibodies. Okay, depending on the level of depending on how unsure the diagnosis is, that type 1 or type 2, which is normally very easy. Okay? In extreme situations, it's hard. You need to do more of those, but usually anti-GAD and anti-ICA, which stands for anti-islet cell cytoplasmic antibodies, are more than enough because they're present in more than 80 to 90% of all the type 1 diabetes patients. Okay, so beta cells release antibodies, autoantibodies directed against our patient's own pancreatic beta cells, okay, and insulin, anti-insulin antibodies, okay. So as you can imagine, progressively, immune system goes on killing these beta cells, destroying them, right? And when the damage to the pancreas, to those islets of Langerhans, reaches a point where more than 80%, more than 90%, depending on the literature, depending on the studies, so more than 80 to 90% of the beta cells are damaged, that's when you see in that patient acute signs of hyperglycemia, acute signs of lack of insulin, which are hyperglycemia, and potentially in type 1 diabetes mellitus, diabetic ketoacidosis following very close by. Okay, so first hyperglycemia, and right after that, diabetic ketoacidosis. Okay, in type 1 diabetes mellitus. Type 2, no diabetic ketoacidosis most of the time. Okay, basically, very shortly after we see first signs of first presentation of type 1 diabetes mellitus, which is usually, unfortunately, diabetic ketoacidosis in younger individuals, right? We see an absolute insulin deficiency, which is very, very sad. Okay, and even our modern day technology has shown that pancreases of patients with type 1 diabetes tend to be smaller and lighter, and they have also like multiple other abnormalities on examination. Okay, so that was pathophysiology of type 1 diabetes mellitus. My next pathophysiology presentation will be dealing with type 2 diabetes mellitus. Okay, hopefully you like it, and hopefully it helps you. Bye now. Take care.